Hello, my name is Sam Harker, and I'll be describing the motion of the helicopter using Desmos here. So I graphed the X and Y components of the position, velocity, and acceleration equations that were found in the video, um, and plotted them on Desmos. This black, this black line off to the left here is the starting time, which is t equals negative t, negative uppercase T. And this black dotted line on the right over here is t equals uppercase T. And as you can see, the graphs don't start at the origin like uh, traditionally they would start. They actually start over here at time equals negative T. So that's an important note. So to describe the motion of the helicopter, I'll just do one component at a time. So I'll start with the X component. As you can see, it starts over here at time equals negative T. And then it moves along the X direction in the positive X direction until time equals positive T. And the rate at which its position is changing is increasing until about time equals 0 at the origin, and then it starts to decrease. And this can be seen over here with our X component of the velocity. The velocity is increasing until it reaches time equals 0, and then it begins to decrease. And something that you can notice is at time equals negative T, the velocity is 0, and at time equals positive T, the velocity is 0. And then moving on, we have our acceleration graph in the X direction. You can see that it is accelerating, which is why it's concave up. And then it is decelerating after time equals 0. Now moving on to the Y direction. This one's a little trickier. We start below the T-axis, and we decided that this meant that the helicopter started in a crater, and then it ends above the T-axis, which means that it lands on a hill. And as you can see, the position is always increasing, which can be shown by the velocity vector. The velocity is never below 0. So the velocity increases and just never stops increasing. It just increases at different rates, which can be shown by the acceleration in the Y direction. Has a positive acceleration and then a negative acceleration right around here. And then it goes to 0 and then becomes positive again as it begins to accelerate, and then starts to decelerate again until the final. So yeah, that's the description of the motion of the helicopter. Thank you.
Now let's make sense of the situation and results presented. The two tasks from the video are to find the time the helicopter spends in the air and where does it land. We know the velocity function is 0 when t equals negative capital T because the helicopter is starting at rest. We also know the velocity function must be 0 when the helicopter completes its flight. So the only other time when velocity is 0 is when t equals capital T. Because the exponent for t is even, the negative input will give the same result as the positive input. Finally, we found where the helicopter landed by subbing in the time interval between the starting point and the final point, which is 2t, into the position function. We believe capital T to be referencing the flight duration of the helicopter. This makes sense for our answer for position because having a bigger T means the helicopter can travel more distance. The motion graphs also have a larger time domain when T increases. The variable t is bounded between negative capital T and positive capital T because they are the roots of the velocity function, and we know the helicopter must be starting at rest and stopping at rest. Now let's figure out the units for the constants alpha and beta. The unit for time will cancel out, so the result of the equation will be meters per second squared for beta, which is a unit for acceleration, and meters per second for alpha, which is a unit for velocity. Beta could be referring to how much thrust the propeller is producing, which is directly correlated with acceleration. By increasing beta, the slope becomes steeper, meaning the helicopter is changing its velocity more rapidly due to having more thrust. Alpha could be the velocity of the propeller, so if the propeller is spinning faster, the helicopter is able to produce more acceleration.
Hello, my name is Nicholas Alves, and this is the reflection portion for Project 1 for Physics 211. In this portion, we will discuss the similarities and differences between the problem we analyzed with problems that we have seen in the studio and lecture. So to start off, one of the main similarities that I have noticed between this problem with the Mars helicopter is how it is similar to the Mario problem that we did in lecture, which involved integrating the function of acceleration of Mario once he finds a superstar over time. And we integrated it to find Mario's velocity and then to find Mario's position over time. Another similarity with the Mario problem is that it made use of constants, as we can see the constant t here in the Mario problem. This problem also used constants, the constant t, alpha, and beta, which we had to find the units for, which was also similar to Mario, and that we also had to find the units for in lecture. Now, another problem that shared quite a bit of similarities, but one main similarity was the Archer problem that we did in studio for, I believe, week 3 of this class. The main similarity was that in this problem, we had to equate variables to find unknown values. In the case of the Archer problem, I believe it was the variable of time, and it was actually the same thing for the Mario problem. This problem, the Mars helicopter problem, where we also solved for time squared, and then we equated it to the x component where time squared was also found. And then from that, we used that to find the distance traveled of the Mars helicopter. Now, one of the main differences that I noticed, at least, to the 2 previous problems and quite a bit of the other problems we did in lecture and studio, is the fact that while alpha and beta are said to be known constants, we aren't given their values, and we aren't given their units, and we also aren't given the units of time and distance. Now, of course, it could be assumed that it's meters and seconds for distance and time, respectively, but that's not something that we wanted to assume. So what we did was we looked up the real-world case of the Mars helicopter, how the range of its distance and time, how long it traveled, how far it traveled for, and then we kind of used that to determine what units best suited the equation, and we found that again to be, of course, meters per second, meters and seconds. Now, that does it for most of the similarities and conclusions. The similarities and differences. So to move on to the conclusion, in this project, Sam Harker, he worked on the actually graphing the equations on Desmos to actually visualize what's going on, and he also analyzed the constants and the components of the vectors. And ChunYew, he compared the results of the equation to the real-world Mars helicopter to see how close it really is to the real thing. He also used graphics to represent the made-up scenarios, and found the units that we were looking for the constants beta and alpha. So with that, this concludes Project 1, our presentation for Project 1, Physics 211. Thank you.